Hi. We've mentioned the normal distribution several times in these lectures, and today we're going to become friendly with it. We're going to learn a little bit more about it. So let's get right to the picture. The normal distribution looks like this. We've drawn pictures of it in the central limit theorem lecture. We drew it many, many times. Sometimes it's skinny, but if you squat it down, you put the scale properly, it'll always look like this. And what it is it's a symmetric distribution about the center, which is the mean. The mean is the center, the expectation of this distribution. The mean is the center of any distribution. But we have a mean in the center, and it sort of goes down. If you're sliding on it, you will find yourself heading down, 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 down. Now, all of a sudden, at one point, you will begin to turn around. Instead of continuing going faster and faster down, you will turn around and start heading up. Not up this way, but at least not falling quite so fast until you slide out and you slide horizontal. At this point where you turn around from going down to going up is called one standard deviation, and the symbol for it is sigma. Sigma, we say it's 1 sigma from the mean. So the point is 1 sigma from the mean on this side. There's another point symmetric on this side, which is 1 sigma from the mean on that side. So the mean plus 1 sigma and the mean minus 1 sigma marks off that place in here where the thing is going down like it was a circle to where it's going up, where it's turning up. And I've marked off not only the mean and 1 standard deviation from the mean, but I've also marked off 2 standard deviations and 3 standard deviations. Because if we look at the distribution, we can just about tell what it looks like by knowing where these marks are. The area, if we take the whole area under the curve, the area under the curve, and the curve goes out like that and eventually hits bottom, or gets so close to it you can't distinguish it from bottom. The area in here, in the central portion, that is the mean minus 1 standard deviation to the mean plus 1 of its standard deviations, contains 70% of the area of the entire curve. Most of it, 70%. Actually, if you really want to be stickler about it, it's just under 69%. But we're gonna say 70% to round things off, nice and neat. Okay, so 70% of the area is in here. If you go between mu minus 2 of these standard deviations and mu plus 2 of these standard deviations, whatever units we have, that the area in this region, the entire region here, is about 95% of the whole thing. That is, there's only 5% outside, 2.5% on each side. If you go out to 3 standard deviations, you've got just about all of the area. There's very, very little outside. In fact, there's less than 1% past the 3 standard deviation mark. That is, from mu minus 3 standard deviations to mu plus 3 standard deviations contains just about all of the area. We say at least 99% of the area. So that's what a normal distribution looks like. It's a bell-shaped curve which inflects, turns from this direction to this direction at 1 standard deviation from its center, from its mean, and then drops down continually till about 3, just after 3 standard deviations, it hits bottom. And 70% of the area is said to be between the mean and plus or minus 1 standard deviation, 95 the mean plus or minus 2 standard deviations, and 99 the mean plus or minus 3 standard deviations. Okay? Now, if we've got that, you're quite familiar with the normal distribution. That's what the normal distribution is. It's a picture, and it's a bell shape, and it changes from this direction to this direction, and that's 1 standard deviation from the mean on each side, and we go 1 standard deviation from the mean, 2 standard deviation, 3 standard deviation, and that's important for you to get that picture because we're gonna use that information later on. Let's get on with properties of this distribution. One of the important properties is how you estimate the mean and standard deviation. Well, we know that the mean and standard deviation are up there in heaven. The mean is the center of all possible data. Well, I don't have all possible data. I have n observations, 100 say. How do I estimate the mean? Well, that's easy. An estimate of the mean is just the average. sum up all the x's you happen to get in your n observations, add them up and divide by n. And we call that x bar, x with a line on top of it, x bar. And that estimates the mean. You'll also see it called mu hat. When you want to estimate something, you write the symbol for it and then put a hat on it to show it's an estimate of it. So an estimate of mu is x bar. Now, if you want to estimate the standard deviation, that is, that's sigma. Remember the standard deviation? It was called sigma. Greek letter sigma looks like an O with a little flag on the end of it. We estimate it with this S. And what S is, take the data you have, subtract the average from each of the data points, and square that distance. That is, it's sort of the, if this were the distance between each data point and its center, this would be the sum of squared distances. And if you had divided by n, you would probably say that's the average sum of squared distances. But we're dividing by n minus 1 instead of m. And the reason for that is rather simple. N minus 1 is called the degrees of freedom. Degrees of freedom. The degrees of freedom relate to the bits of information. The bits of information. Now, what's really happening is when you want to average something like this, you say, oh, I have n observations. Each observation has a bit of information connected to it. I sum up all that information. I divide by how many, and I got the bits of the information per bit. So an average is really the information per bit. Well, if I want to average this up, I have to take the difference between x and its center squared, sum them up, and take the average by dividing this by the number of bits of information. Well, it turns out, because we're using x bar instead of mu, if we knew what mu is, if someone were to call down and tell us what mu is, and we subtracted mu, we would have n bits of information, because x minus mu would have the same information that x had. And square that, we've got a bit of information squared, sum up those bits of information, we divide by how many bits of information, which would be n, and we'd have an estimate of sigma. But no one told us what mu is. So we have to use x bar, estimate of mu. When we use x bar, the estimate of mu, we're essentially using up a bit of information. And that's because, look at this, if I had 5 numbers and I knew what the average was, and someone gave me 4 of those numbers, I could figure out what the 5th number was. They're not independent bits of information. There's only 4 bits of information in a 5-number system, because the last bit of information is included in this. It takes the place of the last bit. So there's really only n minus 1 bits of information, and therefore the degrees of freedom are n minus 1, and therefore I have to find the information per bit. So the degrees of freedom are n minus 1. Now this S estimates sigma for the data. So now we have the estimate of mu and the estimate of sigma. Okay? Now what we learned in the central limit theorem thing was that averages have a normal distribution. Averages, that is x bar. X bar. X bars have a normal distribution. The mean of the normal distribution, the mean of the distribution of the average of this normal distribution, is also mu. How do you know? Well, remember when we saw the pictures, we start out with something, it really didn't matter what it was, and we had a center to it, and then it shrunk around it. Always the center stayed the same. It was always concentrated around the same expectation, around the same mean. Mu was the same for both the original data and for the averages. So we already know that the distribution of the average is normal, which means it's bell-shaped, and obviously, since it's centered about the same center as the original data, and the original data has mu, the mean, as its center, then the mean of the distribution of the averages is mu. Well, right at this point, someone's going to say, well, wait a minute. What do you mean the distribution of the averages, the distribution of x bar? I went here and I have a book, and I made 100 measurements on my book, and I made sum divided by 100, and I have an x bar. Only one x bar. How can one x bar have a distribution? Well, every statistic has a distribution. And the reason for that is you can imagine that Someone took 100 observations on the book. All right, let the next guy take 100 observations on the book. He's got a different value. It's not the same. It's as if you were making a measurement on something. Everyone gets a different measurement. Well, everyone gets a different average because they've taken different measurements. Now, let's say I have thousands and thousands of people all measuring this same book. Now, they come to me with their measurements, and I put them on a ruler, a penny per measurement. What's going to happen is that we're going to end up with a histogram, the usual histogram kind of thing. And when we smooth it out, melt the pennies down, we're going to get a normal distribution. So the average is going to have a normal distribution. Now, I only have one X bar. I can still talk about its distribution. The distribution of the situation where lots and lots and lots of people were to really come up and make an X bar, a different one, and plot it. Now, I only have one, but the distribution is an imaginary thing. It's up there in heaven where you imagine all these people, plotting them, infinite amount of people, infinite amount of data, and when you plot them, you get a distribution. Now, we also know that if you had more observations in your X bar, the distribution would be skinnier, but it would still be normal. All right? So there is a distribution associated with each and every statistic will have a distribution associated with it. And right now we're interested in the distribution of X bar, the distribution of the statistic X bar. There are lots of statistics. We could find distributions of any statistic you like, of sample medians, of the estimate of the standard deviation. We're interested today in the statistic X bar and its distribution. What we know about it is, one, that it's normal. It has a bell shape. Two, that its center is the same as the center of the original data. Well, if we know or can estimate the center of the original data, we sort of have an idea what the center of the normal distribution for X bar is. And now we're going to talk about estimating the standard deviation. The standard deviation of the average is sigma over the square root of n. Well, where does that come from? Well, where it comes from is, I know, let's draw the picture. We know that if we got some data, the data looks like this. And if we take an average of 5, say, the distribution looks like this. It's getting skinnier. Well, what's getting skinnier? The mean is staying the same. The standard deviation of this one was this big. The standard deviation of this one is only that big. It's getting smaller. As you take more and more observations, it got skinnier and skinnier. That is, the standard deviation was getting smaller and smaller. The only question left is what's the rate at which it gets smaller? And of course, I'm not going to derive that here. This is far beyond this class. But I can tell you that the standard deviation of the average is simply the standard deviation of the data divided by the square root of m. That's how it comes out. So in order to get that, to estimate, I just take s and I divide it by the square root of n. And that's my estimate of the standard deviation of x bar. We'll call it the standard deviation sub x bar. That's the standard deviation of the distribution of x bar, right? Which is smaller, and smaller by the square root of 10. As a matter of fact, what is the square root of 10? If I had 100 observations, that would mean that the distribution of the data might look like this, but the distribution of the average is going to be 10 times smaller. Okay? Its spread is going to be 1/10 that of the original distribution when n is 100. When n is 4, it's half the size. It goes up as the square root of the number of observations. Let's take some data. Got some data here. Bunch of data. Now, I can't analyze that data by looking at it. So I asked the computer to analyze it. I said, okay, computer, describe the data. It quickly told me there's 100 observations. The mean of the observations, by the way, it says mean. But what does it mean? It means the average. It takes the average. It certainly can't tell me what the mean is up in heaven, but it says mean because it knows that it's the mean of this data, which is the average of all possible conceivable data. The average of this data is an estimate of the mean of all conceivable data. So 9.852 is not really the mean. It's the average of this data, and hopefully it's close to the mean. The median, it should say, sample median. That's the estimate of the median, and it's 9.9. A little bit different than that, but essentially close to it. This is really the sample standard deviation, or what we call S. When it says standard deviation, it's producing S, which comes from that formula I showed you a moment ago. Now here's an interesting thing. It says SE mean. That's the standard error. Standard error. Or standard error of the mean. Also, what it is the standard deviation of the mean. It is really S divided by the square root of n. That's all it is, S divided by the square root of n. Notice 100 observations, square root of 100 is 10. If you take the standard deviation divided by 10, you get 0.212, standard error of the mean. We use a different name for this because frequently we're interested in the distribution of x bar. And people will say, oh, what's the distribution of x bar? You say, oh, it's normal with mean 3 and standard deviation 4. Well, now that causes a little bit of confusion in people's minds because they think of standard deviation of the original data. If the standard deviation of the average is 4, then the standard deviation of the data must have been bigger. Well, are you telling me the standard deviation of the data is 4 and therefore I have to divide by the square root of n? Or are you telling me that the standard deviation of the average is 4? So I can draw the picture directly. And there's confusion there. And so what we've done in statistics is sort of give a different name to the standard deviation of the average, so that when we say it, everyone knows we mean the standard deviation of the average. And that word is standard error. The standard error. It's nothing different. What it is the standard deviation of the distribution of the average. And if you had the standard deviation of the data, you'd divide it by the square root of n. If what you had was the standard deviation of the average, then that would be the standard error, sometimes called the standard error of the mean or the standard deviation of the mean. And unfortunately, some people, when they talk to you, are going to say standard deviation, and you're going to have to figure out whether they mean the original standard deviation of the data or the standard deviation of the average, which is really the standard deviation of the data divided by the square root of n. And I'll try and be consistent, but you won't always find everybody consistent, so beware. Beware, this thing does happen. Okay, let's look. We have this data in front of us, and the mean is 9.8, let's say 10, and the standard deviation is, let's say 2, just so we can draw pictures nice and smoothly. And the standard deviation of the mean is 0.2, all right? So if we were to draw a picture, sketch a picture of the data without drawing the data, we would put the center of the data about 10, and we'd make a standard deviation 2 units away, 8 to 12. So at 12, we'd put the inflection point, and 8, we'd put the inflection point, and we'd make sure there's about 70% of the data between 8 and 12. Then 2 standard deviations away, that is 8, 6 over here, and 12, 14 over here, we would make sure there's 95% of the data in here. And then by 3 standard deviations, which would take me 8, 6, 4, 12, 14, 16, I would make sure that I've got very little left in the tails, less than 1%. Now that would be a picture of the original data from which the averages I was talking about came. Well, now someone says, draw me a picture of the distribution of the average. Well, I have to be very careful. I know I'm going to have the same center, but I'm going to have a 0.2 instead of a 2 standard deviation. So it would all come out very, very tight in here, 10 times smaller. So what I would do is I would stretch the scale so that the picture would look nice. Now watch the scale carefully as we go from this picture to this picture. The picture stays the same. The scale has changed. So instead of this being 12, it's now 10.2. which is 2/10 of a unit bigger, and 9.8, 2/10 of a unit smaller. And now we have this at the standard deviation. So here's the point at which it inflects. It changes direction. At 10.4, we get 95% of the area. By the time you get to 9.4 and 10.6, you have 99 or more of the area. The picture is identical. If I had drawn two pictures on the same scale. One would be a picture of the normal distribution, and the other would be a picture of the average, and the average would be much, much skinnier. You know, go off the page, much, much taller and much, much skinnier. As it is, this is the picture of the average. If you were to draw a picture of the original distribution, it would be so big, it would be way, way, way off the scale, because one standard deviation is at 12. We only get to 10.6. 12 is down in Chicago. All right? Okay, and I think that's enough for an introduction to the normal distribution, and we will be using the normal distribution quite a bit. It's a good idea you sort of get a feeling for it. Okay?